What is printed circuit board, that is PCB? This video explains about what is printed circuit board. Printed circuit boards are mainly employed to create a connection between integrated circuits, that is ICs, resistors, connectors and other various components. An electronic equipment is a combination of electrical and electronic components connected to produce a certain designed function. In earlier days, the electronic equipment were constructed by hand wiring and by point-to-point soldering. Due to aging, the wires were stripped of their insulation, tinned and soldered. Each discrete component was installed by hand, electrically and mechanically, and the circuit is too bulky and big to manage. So it was difficult to meet the demands for the use of those bulky equipments in aircrafts, the health sector and home emergency uses. At these conditions, it is necessary to develop the smaller and more compact electronic equipments. Smaller components were developed and it decreases the time between unit failure and repair due to easy replaceability. The use of miniaturization and sub-miniaturization in electronic equipment design lead to a novel approach in inter-component wiring and assembly, which is known as printed circuit board. The printed circuit board provides both the physical structure for mounting and holding the electronic components as well as the electrical interconnection between the components. Printed circuit boards are also called as printed wiring board, that is PWB in USA. The classification of printed circuit boards are: digital printed circuit board, analog printed circuit board, mixed analog printed circuit board. Evolution of printed circuit board, that is PCB. This video explains about how the PCB evolved in industry. The history of development of printed circuit boards, still it is not very old. They have been in commercial use only since the early 1950s, but the concept has been originated nearly 50 years prior to their commercial use. In 1904, Mr. Sprague, the founder of Sprague Electric, while still an apprentice, had the idea of eliminating point-to-point wiring. For implementing the concept of silver reduction, he conferred with his mentor Thomas Edison. Mr. Charles Dukas proposed a method in which electrical metal deposits in the shape of conductors are directly mounted onto the insulation material to simplify the construction of electrical appliances using stencil through electrolytic metal deposition. After 17 days later, Mr. Francis T. Harman came with the new subtractive method of making PCBs, which considered as the forerunner of etching technology. In April 1926, a patent was granted to Mr. Cesare Pasolini in France for his invention of the additive way of making electrical connections. In September 1928, Mr. Samuel Charles Ryder filed patent related to the manufacture of inductance coils for use in radio tuning devices or other such applications. For that, he proposed to print a spray the substrate directly with conductive paint during manufacture. Similarly, Mr. Herbert C. Alt in July 1935 in America again emphasized the avoidance of wires as the basic purpose of the development. The major contribution towards the development of modern printed circuit technology came from Dr. Paul Eisler, who proposed copper-clad insulation material in sheet form for use as the base material in circuit board manufacture. He also proposed the generation of conductors on both sides of the copper-clad base material, with connection between conductors on both sides being made through eyelets. So Dr. Eisler is often called as the father of the printed circuit board technology. In the 1960s, the electroless method was introduced using catalyst activators, while Photocircuits USA developed the fully additive process in 1964. In this method, the base material does not have copper on it, and the copper is plated selectively on the required places for interconnections. The size of the printed board got reduced considerably with the manufacture of multi-layer and rigid flexible circuit boards. The continuing trend towards high functionality integrated circuit, that is IC components with higher input-output pin counts of IC packages, has resulted in increased demand for fine-featured PCBs, giving rise to high-density interconnect structures, that is HDIs, which are now manufactured by a large number of companies. Advantages of printed circuit boards. This video pointing out the advantages of printed circuit boards. The interconnections are made through the copper tracks instead of using wires that carries circuit. Much time is saved in assembling a circuit over printed circuit boards compared to the conventional one. As the connections are made automatically through CU tracks, there is no change of loose connection or short circuit. The size of component assembly is reduced with a corresponding decrease in weight. Quantity production can be achieved at lower unit cost. Component wiring and assembly can be mechanized. Circuit characteristics can be maintained without introducing variation in inter-circuit capacitance. They ensure a high level of repeatability and offer uniformity of electrical characteristics from assembly to assembly. The location of parts is fixed, which simplifies identification and maintenance of electronic equipment and systems. Inspection time is reduced because printed circuitry eliminates the probability of error. Printing wiring personnel require minimal technical skills, and training chances of miswiring or short-circuited wiring are minimized. Disadvantages of printed circuit boards. As the copper tracks are very thin, they can carry little circuit, hence a PCB cannot be used for circuit with heavy currents because in that case the strips will be heated up and can cause problems. Soldering needs precautions on the risk of strips being overheated and destroyed is always there. Components of printed circuit boards. In this video, we are going to see the components of a printed circuit board. The essential components of a printed circuit board are base, conductors. Base. The base is a thin board of insulating material which will be rigid or flexible, supports all conductors and components. The base provides mechanical support to all copper tracks and all components attached to the copper. The electrical properties of the completed circuit depend upon the dielectric properties of the base material. Conductors. The conductors, normally of high purity copper in the form of thin strips of different shapes which firmly attach to the base material. The conductors provide the electrical connections between components as well as the solderable attachment points for the same. The conductive areas are usually generated by means of a printing process like screen printing or photo engraving, which are commonly used to print drawings of inscriptions. So the term print became popular, hence it named. Composition of printed circuit boards. In this video, we are going to see the composition of a printed circuit board. In PCB, there are alternating layers of different materials which are laminated together with heat and adhesive, which results a single object. Substrate. The base material or substrate is usually fiberglass. The commonly used fiberglass is FR4. This solid core gives the PCB its rigidity and thickness. Copper. The next layer is a thin copper foil which is laminated to the board with heat and adhesive. On common double-sided PCBs, copper is applied to both sides of the substrate, whereas for lower cost, the PCB may have copper on only one side. Solder mask. The layer on top of the copper foil is called the solder mask layer. This layer gives the PCB its green or red color. It is overlaid onto the copper layer to insulate the copper traces from accidental contact with other metal, solder, or conductive bits. This layer helps the user to solder to the correct places and prevent solder jumpers. Silk screen. The white silk screen layer is applied on top of the solder mask layer. The silk screen adds letters, numbers and symbols to the PCBs that allows for easier assembly and indicators for humans to better understand the board. Silk screen labels are used to indicate what the function of each pin of IC or LED. Manufacturing of printed circuit boards, that is PCB. In this video, we are going to see how the printed circuit board is manufactured. The steps followed in the manufacturing of PCBs are given below. Pre-processing, photolithography, etching, stripping, tin plating, drilling, solder masking, loading of components, soldering. Pre-processing. In pre-processing, all the initial preparation to be made before actual processing of copper-clad laminate starts, which includes layout of the circuit diagram should be taken printout. Cut the copper-clad laminate to the required size using a cutter by placing the printout over the laminate. By scrubbing with steel wool or very fine wet sandpaper, the board is cleaned. The board is made to dry thoroughly. The board should be clean and free from fingerprints or any traces of contamination. Tooling or mounting holes on the board are drilled. Step 2. Photolithography. Photolithography is a process of transferring the copper track and land pattern from the negative film to a photosensitive material by exposing selectively to a radiation source such as UV light, which includes the following steps. Pattern transfer. Applying photoresist, copper surface of the copper-clad laminate is coated with a photosensitive material by using dip coating machine. In lithography, the photosensitive material used as a photoresist, which is also known as resist. Both positive and negative photoresist can be used, but negative photoresist, which become insoluble on exposure to UV light, is almost universally used. Photoresist coated board is placed in the oven for 10 minutes for the purpose of drying the photoresist. Exposure to UV light. The board is removed from the oven and placed it in ultraviolet exposure machine with the photoresist side facing up. Now the mask, that is the negative film, is placed over the board and correctly aligns it with the board's geometry. The UV light falls on the photoresist only through the lighter or transparent part of the mask. To keep the negative film in position, masking tapes are used. The UV exposure machine is switched on for 3 minutes. Thus, the photoresist changes its properties only where exposed to radiation. Take out the boards from the UV enclosure by holding it from the edges, that is, using forceps. Development. After exposure, the pattern's image is transferred on the photoresist and to be developed. The development stage involves 2 steps based on the type of resist. For negative resist, unexposed areas of resist are removed. For positive resist, exposed area of resist are removed. Here, we are explaining a negative photoresist method. In a tray, a sufficient developer solution is poured such that the board can be completely dipped in it. Developer solution is prepared by mixing liquid photoresist developer concentrate of 1 part with 9 part of water. The board is placed into the white developer solution. the board should be handled at its corners with the help of forceps. Now the tray is lifted on each side in rotation so that the liquid developer is flowed over and back on the board. This is continued throughout the developing time, that is 1 minute. During development, the unexposed region of the negative photoresist is etched away by the developer solution, showing copper pattern, and the PCB layout will be visible. After the development is over, board is lifted and washed in stop bath. This will effectively stop the development action. Fixing. To fix the pattern on the board, 1 cap of blue dye solution, that is fixer, in 1 glass of water in a tray is mixed. The board is placed in the solution for at least half minute and the board is removed from the fixer bath and washed under running water. Step 3. Etching. This process is used for removal of a PCB's copper surface, which is not protected by the photoresist. Thus, the final copper pattern is formed on the board after etching. The board obtained after photolithography is dipped in an etching solution and agitated for 6 to 10 minutes at 40 degrees Celsius. The solution etches or dissolves away the exposed or undesired copper areas, leaving the desired copper pattern on the board. Ferric chloride is the most commonly used etchant. Step 4. Stripping. The negative photoresist coating left on the copper pattern can be removed using a tube of photoresist stripper after etching process. And the PCB is washed under tap water and dried using tissue paper. Step 5. Tin plating. Tin plating is the process of providing a fine finish and the protection to the copper from oxidation, which aids soldering to appear neater and to flow better. A fine tin powder is mixed with water to make up a solution in a basin. The board is placed in the solution for 10 minutes to have a silver finish on the board. Step 6. Drilling. Drilling is a process employed to create the component lead holes and through holes in a PCB. These holes pass through the land areas and it should be positioned correctly. The drilling process can be performed either manually nor programmed CNC drilling machines. Once drilling is done, though there is a physical path exists between pads on different layers, but there won't be any electrical connection between them. To make electrical connections between pads on different layers of the PCB, the board is placed into a plating bath. The plating bath coats the inside of the holes of the PCB with copper, which electrically connects the pads, so-called plated through holes. The clearance is larger than the normal pad size to ensure that the plane stays isolated from the plated holes. Solder masking. Next, a thin polymer layer is usually applied to the top and bottom of the board. This layer is called the solder mask or solder resist. Holes are opened into the polymer where the components will be soldered to the board. To expose the pads and holes, photolithography method is used. The solder mask protects the top and bottom copper pattern from oxidation and helps prevent solder bridges from forming between closely spaced pads. Finally, silk screen markings are placed on the board to identify the position where components are to be placed. The silk screen marked in white. Step 8. Loading of components. Loading of components can be done manually or automatically. Manual assembly. Manual assembly can be tedious work and is typically used for prototype and low volume work. In post-automated assembly for odd form components, manual assembly is used. Both surface mount technology, that is SMT, and through-hole technology, that is THT components may be assembled manually. In low volume work, an assembly line consists of several assemblers in which each person is responsible for mounting specific components. Manual assembly may involve both manual placement and soldering of the specific component, or a mixture of manual placement and automated soldering of the component attached, which can be interrupted several times. Automated assembly, that is pick and place. Automated insertion processes, that is pick and place, exist for both surface mounted devices, that is SMD, and through-hole devices, that is THD, which include both axial leaded and radial devices. Automated machines are programmed to extract parts or components from the reels or bins and place the components on the PCB in the correct location and orientation. By using automated assembly, through-hole devices can be assembled at rates from 20,000 components per hour, that is CPH, to 40,000 CPH. Soldering. Soldering is used to attach the components physically to the PCB and also to provide electrical conductivity between the components' leads and the PCB traces. An intermetallic compound or alloy must be formed between the solder and the base material, that is, the leads and traces, in order to the soldering process to be successful. To protect the solder joint areas from oxidation, contact areas of the PCBs are being dipped in a solder bath to receive a surface finish, and hot as solder are plated by plating process such as electroless nickel or palladium. Just prior to or during soldering, the surfaces to be joined are cleaned, that is deoxidized, with flux so that the solder can flow over PCB neatly and wet the surfaces of the PCB. There are two general soldering methods. Mass soldering, that is, which includes wave reflow, vapor phase reflow, oven reflow, and conduction reflow. Directed energy, that is, which includes hot gas, hot bar, laser, iron, and pinpoint torch. Single-sided printed circuit boards. This video explains about the single-sided printed circuit boards. In single-sided printed circuit boards, single-sided means that the wiring will be available only one side of the insulating substrate. This type of boards is mostly used in the case of simple circuitry for which the manufacturing costs are kept at a minimum. The side contains the circuit pattern known as solder side, whereas the other side is called component side. The single-sided boards are manufactured by either the print and etch method nor by the die-cut technique. By using a die which carries an image of the wiring pattern, and the die is either machine engraved or photo engraved. Normally, components are used to jump over conductor tracks. If it is not possible, jumper wires are used. The number of jumper wires on a board cannot be accepted beyond a small number due to economic reasons, which results in the requirement for double-sided boards. Double-sided printed circuit boards. This video explains about the double-sided printed circuit boards. In double-sided printed circuit boards, double-sided means having the wiring patterns on both sides of the insulating material. Thus, the circuit pattern is available on both component side and the solder side. Compared to single-sided boards, the component density and the conductor lines are higher in the double-sided boards. Two types of double-sided boards are commonly used. They are double-sided board with plated through-hole connection, that is PTH, and double-sided board without plated through-hole connection, that is non-PTH. Double-sided PTH board. Double-sided PTH board has circuitry on both sides of the insulating substrate. Both the sides are connected by metallizing the wall of a hole in the substrate, which intersects the circuitry on both sides. This technology is the basis for most printed circuits produced. This kind of board is popular where the circuit complexity and density is high. Double-sided non-PTH board. Double-sided non-PTH board is an extension of a single-sided printed circuit board. Its cost is considerably lower because of the plating. In double-sided non-PTH board, through contacts of the components are made by soldering the leads of the component on both sides of the board wherever necessary. The number of solder joints on the component side should be kept to a minimum at the layout design of boards. This is to facilitate component removal in the board if required. The conductor should be realized on the non-component side as much as possible, and only the remaining components should be placed on the component side. The non-plating technique is double-sided boards is shown in which the interconnection is made by a jumper wire. A formed insulated solid lead wire is placed through the hole, clinched and soldered to the conductor pad on each side of the board. Different types of eyelets are also used for double-sided board interconnection. They are funnel flanged eyelet, split funnel flanged eyelet, fused in place eyelet. The difference between non-plated through hole and plated through hole. The presence of plated copper inside the insulating base material. The presence of this plated through hole has in turn effect on electrical properties. Plated through holes PCB is more costly than the non-plated through hole PCB. Plated through holes PCB consumes less space or area than the non-plated through hole PCB. The advantage of using non-plated through holes come from simpler and maybe quicker manufacturing. Multi-layer boards. This video explains about the multi-layer printed circuit board and drawbacks of plated through hole technology. Multi-layer boards. The multi-layer board makes use of more than 2 printed circuit boards with a thin layer of pre-preg material placed between each layer to make a sandwich assembly. The printed circuit on the top view is similar to a conventional printed circuit board assembly, except that the components are placed much closer to each other, or they may have many terminals, which insist the use of additional board layers for the required interconnections. The electrical circuit is completed by interconnecting the different layers of PCB by plated through holes, places transverse to the board at allotted places. In multi-layers PCB, all the interconnections can be placed on the internal layers of the PCB, and a heat sink of thick solid copper can be placed on the outer surfaces of the PCB. By mounting the components directly on the metallic surfaces, the problem of heat removal and heat distribution in systems can be minimized. Rigid and flexible printed circuit boards. This video explains about the rigid and flexible printed circuit board. Printed circuit boards can also be classified on the basis of the types of insulating material used, that is, rigid and flexible. While rigid boards are made of a variety of materials, flexible boards use flexible substrate materials like polyester, polyamide, etc. The base material is usually very thin, which is in the range of 0.1 mm thickness. Laminates used in flexible boards are having the copper on one side or both sides of the rolls. Rigid flex PCBs, which constitute a combination of rigid and flexible boards usually bonded together. These boards are three-dimensional in structures that have flexible parts connecting the rigid boards in order to support components. 4-layer rigid flex circuit. A 4-layer combination rigid flex circuit has 4 conductive copper layers. Typically, a 4-layer has 2 flexible layers and 2 rigid layers. 6-layer rigid flex circuit. A 6-layer combination rigid flex circuit has 6 conductive copper layers. The two most common design types are as follows: 6-layer rigid flex, 2 flex layers and 4 rigid layers, 6 layer rigid flex, 4 flex layers and 2 rigid layers, 8 layer rigid flex circuit. Rigid flex circuits combine the best of the both rigid boards and flex circuits integrated together into one circuit. The 2-in-1 circuit is interconnected through plated through holes. Rigid flex circuits provide higher component density and better quality control. Designs are rigid where extra support is needed and flexible around corners and areas requiring extra space. What is an artwork? This video explains about what artwork is. Artwork is a manufacturing tool used in fabricating the printed wiring because it uniquely defines a pattern to be placed on the board. Artwork displays only those items that have to be generated as copper patterns in the manufacture of the PCB. Therefore, the artwork will necessarily include solder pads, lands and conductors true to scale in respect of their dimensions but shown at the scaled level. In addition, the artwork will also show lines that represent the boundary of the board. Since the artwork is the first step of the PCB manufacturing process, it has a great influence on the final product. Obviously, the final product call only approves the quality and accuracy of that of the artwork. The generation of artwork to the request sophistication is highly dependent upon the area, that is board size and accuracy. Therefore, the importance of a perfect artwork should not be underestimated. Problems like inaccurate registration, broken annular rings, or too critical a spacing observed on the PCBs often occur due to bad artwork. Developing a clean and exact artwork necessitates skills and patience on the part of the personnel entrusted with the task. Artwork generation for single-sided boards is a straightforward exercise, but for preparing artwork for double-sided printed circuit boards leads to a problem in securing accurate registration between the two sides. In multi-layer boards, due to improper alignment, shorting between layers may occur when the board assembly is drilled for plated through holes. Photographic film. This video explains about the photographic film which is involved in film master preparation. Film master is prepared from the artwork, which will be film negative or film positive, which is finally used for the direct exposure of the photoresist coated PCB or the light sensitized screen. In order to ensure PCBs of high quality, the film master must have dimensional accuracy, sharpness, wear-out resistance. The final quality of the film master in general depends upon the chemicals, the film emulsion and exposure units such as cameras. How it is prepared. Film master preparation follows the process given below. Photographic film, film exposing through cameras, film processing in darkroom, Film development. Photographic film. The photographic film basically consists of two layers, the emulsion and the base. The emulsion is responsible for the photographic properties of the film, has an approximate thickness of 5 to 10 micrometer. When unexposed, the emulsion has light-sensitive silver halides that are stabilized in halide or in a synthetic suspension. Base. The material of the base can be acetate, polyester of glass, and has thickness of 100 to 250 micrometer. The dimensional stability of the film is primarily decided by the material of the base. The dimensional changes are usually expressed in ppm, that is part per million. For highest dimensional stability, glass-based film is used. If the dimensional stability is not much of a concern, acetate-based film can be employed. Reproduction film is used to obtain a negative or positive photo tool from the artwork, with or without photo reduction through camera exposure. Duplicating film is used to obtain either a negative from another negative or to obtain a positive from a positive master. The image is transferred by contact exposure or by camera exposure without reduction. The base thickness and the process are the same as for the reproduction films. Diazo film is entirely different from the silver gelatine films, which is opaque to ultraviolet light but transparent to normal light after exposure and developing. This does not require a dark room for exposing. Films are exposed using a camera or contact exposure units. This film is developed by passing through a vapor of ammonia. It does not need any chemical bath for developing and the film dries very fast. Factors affecting the photographic film. The variation of temperature in the surroundings or storage area affects the dimensional stability of the film. Exposure to direct sunlight will lead to poorly processed print. This results in the formation of stains and the film may fade. Gaseous impurities like nitrogen oxide, sulfur dioxide, hydrogen sulfide and ozone react with the silver in the emulsion, resulting in faded images which also tend to decompose the base material. Hence, the film should be stored away from the above impurities. Handling of films is very important as improper handling damages the film emulsion. Films should be held only at the edges. Thin cotton hand gloves are also recommended for handling. Film exposing through cameras. This video explains about the film exposing through cameras. The camera is used for exposing photographic films to achieve color separation and photo reduction. The camera should have flashlight units, reduction lens system and a vacuum system. Accurate exposure time control. Conveniently accessible focus and operative control. Flat field type of lens. Free of spherical aberration. Color corrected and essentially distortion-free image. The camera should be mounted on vibration-free mounts in a processing room or darkroom. The image formed on the photographic film depends upon the camera resolving power of the lens and light intensity. The exposure time depends upon the light source. Cameras are of two types. They are vertical reduction camera and horizontal reduction camera. The horizontal camera basically permits bigger artwork and film sizes, whereas the vertical camera needs comparatively lesser floor space, but the copied board size is limited to enable a normal standing person to operate the camera conveniently. Working principle of the camera: lamp, illumination optics, diffuser, test chart, diaphragm, shutter, reference surface, photographic material, vacuum bag. Film processing in darkroom. This video explains about the film processing in darkroom. Film processing requires a darkroom. All photographic films are light sensitive and hence the darkroom should be light proof and air conditioned. In order to ensure that the dimensional stability requirements of the film are met, the temperature and humidity inside the darkroom should be kept within the permissible limits along with the safe lighting. Generally, the temperature of the darkroom is maintained at 20 degrees plus 2 degrees Celsius and the relative humidity around 55% plus or minus 5%. A slight atmospheric overpressure inside the darkroom prevents dust from entering through the doors and windows. The occurrence of vibrations in and around the darkroom should be avoided, and this has to be considered right at the planning stage of the layout of the building. Darkroom should have separate provision for the storage of films and chemicals. The processing room and the film dryer unit should be provided with running water facilities. It is preferable to have two sinks with running water, one for rinsing the film and the other for washing of hands, etc. The film processing room should be illuminated with safe light with filter. The type of safe light depends upon the type of film used. The safe light should not sensitize the film emulsion. Normally, yellow, orange or red light of 15-watt bulb is used. It must be mounted at least 120 cm away from the film processing area. The photographic films consist basically of two layers, namely the emulsion and the base. The emulsion is light-sensitive silver halide. The light-sensitive chemicals are reduced or oxidized by light with a wavelength of 360 nanometer to 680 nanometer falling on the surface. This wavelength region determines the sensitivity of the photographic film. In the visible region, yellow, orange and red spectrums do not affect the film emulsion. Therefore, these colored lights are used as safe lights in the dark room. Some useful items needed in the dark room work are trays of suitable size for developer, stop bath and fixing, They could be a plastic or stainless steel. Film forceps to handle film during processing. Bath thermometer. Darkroom alarm clock. Refrigerator for storage of unused film. Storage space for artwork. Film development. This video explains about how the film is developed. The films are affected by any natural or bright light source. Film processing should be carried out only in the dark room, which is lighted with safe lamp of low intensity lighting. The photographic film development process is explained in below shown figure. The artwork is placed on the trans-illuminated copy board of the camera. The camera is adjusted to obtain a sharp distortion-free image of the artwork in a 1:1 standard scale. The photographic film is indexed on the film plane of the camera and held under the vacuum. This film is then exposed for the required time depending upon the type of film used. The exposed photographic film is removed and developed by following the steps given below. Silver bromide in gelatin is sensitized by light radiation, which produces metallic silver and bromide iron that will dissolve in the fixer. AgBr gives Ag plus Br minus. Bath sequence of film development. Developer bath, stopper bath, fixer bath, washing process, drying process. Developer bath. After exposing, the film is immersed in a solution of mild reducing agents like pyrogallic acid mixture called developer. The parts that have been exposed to light are reduced to metallic silver more readily than the unexposed parts. The developer is a mixture of chemicals dissolved in distilled or deionized water. The developing time depends upon the concentration of the chemicals and the agitation of the bath. Stopper bath. The function of the stopper bath is to effectively stop the development action. After the development is over, the film is lifted above the developing tray for a maximum period of 3 seconds, which enables the excess developer to drop, followed by immersion in the stopper bath. The film is immersed for about 30 seconds in the stopper bath, consisting of dilute acetic acid maintained at a temperature of 20 plus or minus 2 degrees Celsius. The stopper bath also needs moderate agitation. Fixing bath. After developing, the unexposed grains are dissolved in the fixing bath, which contains a sodium thiosulfate mixture. The bright part of the object develops dark spots on the film, and the film is called a negative film. For fixing the emulsion properly, the film is immersed in the fixing bath. The following chemicals are used in the fixing bath: sodium thiosulfate anhydrous, sodium metasulfate anhydrous, boric acid, that is crystals, sodium acetate anhydrous, aluminum potassium sulfate, that is alu, and distilled water. The temperature of the bath should be maintained at 20 plus or minus 2 degrees Celsius. The fixing time depends upon the bath concentration and agitation. Normal light in the dark room may be switched on after disappearance of the milky emulsion. Washing and drying. After fixing is done, the film is washed in running water at 20 plus or minus 2 degrees Celsius till all the suspended solids are dissolved. The film is preferably dried at room temperature and takes about 1 hour to dry. The use of water filter with a porosity of 50 micrometer with the tap water is recommended to avoid damage to the film from solid matter that may be present in the tap water. Anatomy of laminates. This video explains about the laminates and its parts. Introduction to laminates. Laminates for PCBs are composite materials. Laminates are the products obtained by the process in which the filler material layers impregnated with resin is pressed under the heat and pressure. The primary function of the laminates are to provide the mechanical support for electronic components as well as to interconnect the electronic components electrically. The resulting thin insulating material, that is laminate, the mixture of filler, that is reinforcement, and resin on which all the conductors and components are mounted, is known as base material. This can be either rigid or flexible material. Fillers, that is reinforcements. Fillers are meant to provide stability, mechanical strength, and rigidity to the laminate. Commonly used fillers are a variety of papers, cotton fabric, asbestos sheet, glass in various forms such as cloth, continuous filament mat, ceramic material, molybdenum, etc. But the most common materials used are paper and glass fiber. Resins. Resins are used to impregnate the selected fillers. They are mostly synthetic types of materials formed by the polymerization process, which is either thermoplastic or thermosetting. To achieve higher thermal properties or improved chemical resistance, epoxy resins are modified with additives. Copper foils. The conductive layer on a laminate is made of copper, beryllium copper, nickel, stainless steel. The most widely used substance to coat over the laminate is copper due to its easy availability, cost, and functionality. Copper cladding can be made on one side or on both sides of the composite, depending upon the need and use. The quality of PCB depends on the properties of the copper foil, which leads to the quality requirements of copper foil are very demanding. Copper foil must satisfy strict quality requirements. This resistivity should be 0.1594 ohms gram per meter square at 20 degrees Celsius. The foil should be free from pits, pinholes, nodules, and scratches. Forms of copper foils. This video explains about the forms of the copper foil. Copper foil is available in two forms: rolled annealed copper foil and electrolytic copper foil. Rolled annealed copper foil. The rolled copper is mainly used in the flexible PCB manufacturing process. The rolled annealed copper foil is manufactured by melting electrolytically formed copper cathodes into large ingots. To get large copper foil rolls, the ingots are hot rolled in a specially designed rolling mills and annealed. Even though foil manufacturing is easier, it has some disadvantages like limited width, poor solderability, adhesion and ductility problems which are created due to grain structure deformation. The rolled copper foils which are produced by annealing electro-deposited copper at a high temperature are known as high temperature elongator, that is HTE foils. Electrolytic copper foil. Electrolytic copper foil is manufactured by the electroplating method. The tank has polished stainless steel or lead rotating drum which acts as a cathode and pure copper as the anode. Both anode and cathode are immersed into the copper sulfide electrolyte. Anode, copper solution, stainless steel rotating drum, that is cathode, copper foil, blade, copper foil roll. The depositor copper is easily peeled off because of poor adhesion on the polished drum, which has a very smooth shiny finish on one side and dull finish on the other side. Using suitable adhesives, the dull side increases its adhesion. The grain structure size is vertical in nature and gives excellent bond strength. In order to improve adhesion, the dull side of the copper is again subjected to further process to increase the roughness by chemical oxidation. The advantages of thin foils include very rapid etching time, less etchant waste, elimination of bonding treatment prior to photoresist application, better photoresist adhesion. Materials needed for manufacturing of copper-clad laminates. This video describes about the materials needed for manufacturing of copper-clad laminates. Materials needed for manufacturing of copper-clad laminates. Copper-clad laminates are manufactured by pressing layers of filler material impregnated with resin under heat and pressure with copper foil using a hydraulic press. The materials needed for the manufacture of laminates are glass fabric, that is filler, epoxies that is resin, fiber glass cloth. In most laminates, glass cloth acts as the main structural reinforcement. The rigidity and strength offered by glass cloth enhances the binding, encapsulating and insulative properties of the epoxy resin. The singular fiberglass filament is the building block. Using these glass cloths are constructed together to form a yarn or bundle. Epoxy resins. The functions of the resin is to function as a glue to hold or impregnate the laminate together. Epoxy resin in a liquid form used to concoct to upstaged resin using proprietary recipes and processes. Copper foils. Most commonly used copper foil is FR4, which are manufactured by electrodepositor type. These are made by plating copper onto slowly revolving drum-shaped cathodes that are partially immersed in the plating solution. As the drum revolves, the plated copper deposited is removed from the cathode drum at one continuous speed. Varying the drum speed and current density helps to vary the copper going to be deposited and consequently the resulting foil thickness. At this stage, the raw foil is then subjected to various processes designed to increase the roughness of the matte side so as to increase its mechanical adhesion to the substrate. In addition, the foil is coated with a micro-thin film of protective coating to prevent oxidation of the copper during lamination and storage. Manufacturing process of copper-clad laminates. This video explains in detail about the manufacturing process of copper-clad laminates and its steps. The three primary raw materials for manufacturing copper-clad laminates are glass, resin, copper. The raw materials are pressed at the laminator to give a fully cured final product that is dimensionally stable and resistant to moisture, chemicals, and thermal excursions occurring in the PCB manufacturing process. The process utilized in bringing the thin major raw materials together to form a copper-clad laminate. Treating. Treating is the process in which the liquefied resin is applied to the glass cloth via a combination of immersion and metering rollers. The treated cloth is then subjected to a controlled heat source, then to semi-cure the resin. The heat source is a drying oven, which will be air circulating type or infrared type. Most of the volatiles are driven. Impregnated glass sheet is now dry to the touch, and this stage is generally referred to as pre-preg or B stage. During treating, as the immersion and metering process are critical, rigid process control is necessary. Thorough wetting of the glass cloth by the resin leads to the precise control of the resin quantity absorbed are of utmost importance of the laminate consistency and quality. Layup. Layup is the process of assembling the treated prepregs and copper foils to be pressed. In this operation, the copper foil is first laid against a large polished stainless steel press plate, then a number of sheets of prepregs are laid on top of the copper, the number of layers based on the desired thickness of the laminate. The final sheet of copper foil is placed on top of the prepreg if the material is to have copper on both sides. If copper is desired only on one side, a release film is used to replace one of the sheets of copper. Pressing. Pressing is a process in which the heat and pressure are applied simultaneously to the packs or books, that is prepregs, copper foils and release film, etc. to produce fully cured laminates. This operation is carried out in a press which is hydraulically operated and capable of developing pressure up to 1000 psi. Steam is a typical heat source. Packs or books are loaded into each press for molding. During pressing, the semi-cured epoxy resin liquefies and flows, expelling any entrapped air or gases. This flow acts to encapsulate the treatment side of the foils, to facilitate foil adhesion, to homogenize the resins in each laminate. After a certain period of time, the epoxy groups in the liquefied resin begins to form crosslinks, leading to curing of resin. Thermocouples are placed in several sheets to monitor and control temperature, while a timer automatically records time against a preset cure cycle. When the curing is completed, the steam is automatically cut off. Press cooldown begins and the press books are cooled to a temperature 80° Fahrenheit. The edges are trimmed from the sheet to remove the irregular excess resin flow areas after removing the material from the press. At this stage, the laminate sheets are sheared down to the desired sheet or panel size. Quality control. During the manufacturing process, several quality control checks need to be implemented to ensure uniformity in thickness of the laminate, lamination integrity, that is endurance of extreme thermal, mechanical and chemical abuses, bow and twist, surface quality and dielectric variations. Knowledge of the laminate manufacturing process will be helpful for designers, fabricators and assemblers in understanding the capabilities and laminations of this critical building block of PCB manufacture. After the laminate has been formed, it undergoes various tests. They are conducted to check for the following: cleanliness, warp and twist, dents, flame resistance, scratches, dimensional stability, thickness, resin content, water absorption, volatile content, solder float test, that is solder resistance, resin flow and gel time, bonding strength, printability, flexural strength, drillability, peel-off test, punching and shearing qualities. Properties of copper-clad laminates and IPC standards of laminates. This video explains about the properties of copper-clad laminates and IPC standards of laminates. The properties of laminates vary from grade to grade depending upon resins and fillers. The electrical, mechanical, chemical and thermal characteristics of laminates mainly depend upon the selection of the resin. The electrical and mechanical properties of laminates are affected by environmental factors such as humidity, temperature, corrosive atmosphere, etc. The important properties of laminates are explained below. The electrical properties of a laminate depend upon the electrical properties of the filler, cured resin, and the byproducts of the curing reaction. When exposed to high humidity conditions, laminate absorbs moisture to some extent. Consequently, this absorbed moisture greatly affects the electrical properties. Dielectric strength. This is the ability of an insulating material to resist the passage of electric current of a disruptive discharge produced by an electrical stress. It depends upon a large number of factors pertaining to the material such as chemical composition, molecule structure, degree of moisture, thickness, cleanliness, roughness of surface, material aging. Before it is placed between two electrodes, the test is performed by applying 50 Hz AC voltage on a piece of laminate whose copper surface is to be etched off. Dielectric constant. Dielectric constant is the ratio of the capacitance of a capacitor with a given dielectric to the capacitance of the same capacitor with air as dielectric. It is calculated from the capacitance as read on a capacitance bridge, the thickness of the sample and the area of the electrode. The dielectric constant is also referred to as permittivity, and it measures the capability of an insulating material to store electrostatic energy. It varies with the thickness, temperature, humidity and frequency and chemical composition of the material. Dissipation factor. The dissipation factor of an insulating material is the ratio of the total power loss, that is in watts, in the material to the product of the voltage and current in the capacitor in which the material is the dielectric. The dissipation is directly related to the resistive power loss in a laminate. Therefore, laminates with a low dissipation factor can be used for an electronic circuit operating at a higher power loss. The dissipation factor of a laminate varies with the frequency changes, temperature changes, and amount of moisture absorbed as follows. Increase in frequency results in decrease in the dissipation factor. Increase in temperature results in increase in the dissipation factor. Increase in moisture constant results in proportional rise in the dissipation factor. Insulation resistance. Insulation resistance is the ratio of the voltage applied to the current flowing in the base laminate. The change in resistance under a specified environmental condition is usually more significant. Insulator resistance varies with the environmental conditions and the process techniques of the test samples. During testing of the insulation resistance, the test specimen should be placed in the same environment as would be available in the final application. Surface resistivity. Surface resistivity is the resistance to electrical leakage current along the surface of an insulating material. This depends upon surface humidity, cleanliness, finish, temperature, and environmental conditions, among other things. The surface resistance between 2 points on the surface on any insulation material is the ratio of the DC potential applied between the 2 points to the total current between them. This is measured by using a 3-electrode circular system as shown in figure. The electrodes are formed by removing the metal foil completely by etching, but leaving the foil outlines on the specimen to form the edges of the electrodes. The guard electrodes on the opposite, kept at positive potential, help to avoid stray currents passing through the laminate. Measurements are made by applying 500 volt DC voltage with a megaohmmeter. Surface resistivity also indirectly depends upon the chemical composition of the dielectric material. The material with high moisture absorption property results in a reduction of surface resistivity. The effect of humidity on the surface resistivity of glass epoxy have been found to decrease logarithmically with an increase in humidity. Volume resistivity. Volume resistance is the ratio of the DC potential applied to electrodes embedded in a material to the current between them. It is usually expressed in ohm centimeter. The volume resistance is again measured by using the 3-electrode method as shown in figure. Volume resistivity depends upon the factors such as the chemical nature of the material, temperature, and moisture absorbed in the sample. Dielectric breakdown. Dielectric breakdown is a disruptive charge measured between 2 electrodes inserted in the laminate on 25.4 mm centers perpendicular to the lamination. The test is carried out in oil in a similar manner like measurement of the dielectric strength. Standards of laminates. IPC 2531 Standard Recipe File Format, that is SRFF specification, outlines the requirements that our SRFF file must meet, describes the file format, outlines the file sections and indicates how data should be represented through objects which can either be vendor independent or specific. IPC 2547 Sectional requirements for shop floor equipment communication messages, that is CAMX, for printed circuit board test, describes event message content, and an XML encoding scheme which enables a detailed definition of messages in the domain of electronics inspection, test, and repair or rework, that is product and process quality. IPC 2571 Generic Requirements for Electronic Manufacturing Supply Chain defines an XML encoding scheme to facilitate supply chain interactions. The scheme is defined for bill of materials, approved manufacturer list, changes in engineering, manufacturing or product. IPC 2511A Generic Requirements for Implementation of Product Manufacturing Description Data and Transfer Methodology identifies the generic requirements for implementation of product manufacturing description data and transfer, helps user to transfer design requirements and manufacturing expectations from computer-aided design systems to computer-aided manufacturing systems for printed board fabrication, assembly and test. IPC 2511B Generic Requirements for Implementation of Product Manufacturing Description Data and Transfer XML Schema Methodology specifies the XML scheme that represents the data file format to describe printed boards for tooling, manufacturing, assembly inspection and testing requirements. IPC TR 485 Results of Copper Foil Rupture Strength Test Round Robin Study. The test report evaluates rupture strength testing as a means of determining the mechanical properties of electro-deposited and rolled copper foil. IPC 4412 Specification for finished fabric woven from e-glass for printed boards covers the classification and requirements for finished fabrics woven from e-glass fiber yarns. IPC 4130 Specification and Characterization Methods for Non-Woven E-Glass Mat defines the nomenclature, definitions and requirements for materials made from non-woven e-glass fibers, includes specification sheets for selecting and purchasing these materials. PC 4110 Specification and Characterization Methods for Non-Woven Cellulose-Based Paper for Printed Boards defines the nomenclature, chemical and physical requirements of paper made from cellulose fibers for PCB fabrication. IPC 4411K Specification and Characterization Methods for Non-Woven Para-Aramid Reinforcements includes the nomenclature, definitions and requirements for reinforcement made from non-woven para-aramid fibers. Image transfer techniques. In this video, we are going to see the image transfer techniques following in the market. Image transfer basically involves the process of the transfer of the conductor pattern from the film master onto the copper-clad base material or any other metal-clad laminate. In the fabrication of the PCB, the two methods common for image transfer are photo printing method, screen printing method. Photo printing. Photo printing is an extremely accurate process which is generally applied to the fabrication of semiconductors and integrated circuits. Such a precision technique is not required in the production of general-purpose PCBs. Screen printing. Although less precise than the photo printing process, screen printing is a comparatively cheap and simple method. The majority of PCBs produced worldwide are screen printed. Photo printing. Photo printing of PCBs basically means applying photosensitive material having the ability to form a continuous film which is sensitive to light or other radiation so that the exposed or unexposed areas of the film can be further processed without affecting the unexposed or exposed areas. This photosensitive material is called photoresist. The essential property of a photoresist is that an exposure to proper radiation should produce a change in it to enable a clear distinction in the later operations between the exposed and unexposed areas. The photoresists are sensitive to ultraviolet light with a wavelength of 200 to 500 nanometer. Like the photofooting film, the photoresist has a safe visible light area in the yellow to red wavelength, that is 560 to 700 nanometer. Photoresist can be classified as wet film, that is liquid film, and dry film, that is solid film resist. Photo printing method. This video explains in detail about the photo printing method and the types involved in it. Irrespective of type of resist used, the following steps are applied for image transfer with the photo printing techniques. The coated board is exposed through the appropriate positive or negative film to ultraviolet light. Double-sided exposure is made by ensuring that the patterns on both sides are aligned by matching up special punch holes on the boards and photographic film if the board is double-sided. Exposure times can range from a few tenths of seconds to several minutes. The resist is again developed, leaving those portions of the copper to be retained on the board covered by the resist. In the case of liquid resist, two additional steps are employed. They are applying a dye to the resist so that it is visible on the board, baking the resist at about 80 to 100 degrees Celsius for 10 minutes so as to harden the resist before the etching process. Liquid photoresist, that is wet film resist. The wet film resist are organic liquids. When it is exposed to light of a proper wavelength, chemically change their solubility to certain solvents, that is developers. The factors that help to determine the correct chemical and physical performance of the wet film resist are the chemical constituents, the mixing ratios, the residual solvents, monomer levels. The wet film resist is coated on the laminate by several techniques such as dip, spray, roller coating, flow, dip. The board is dipped into the resist and pulled out slowly. The coating is usually thicker at the bottom of the board than the top. Spray. Thin coatings of desired thickness can be made by using spray technique. The use of multiple spraying can build up the coating thickness. Double-sided systems can coat both sides with an appropriate carriage system, which can continue to carry panels through a drying oven. The system loses material through overspray, so this method is not currently used. Roller coating. Roller coating technique is done in a special two-sided roller coating equipment which is directly coupled to a drawing system without releasing the panel. Surface uniformity over a large panel is good. flow. The resist is placed on the board and is gently tilted till the resist covers the whole board. The method is useful for large area boards. After applying, the resist is normally baked at 80 degrees Celsius for a few minutes so that it is hardened. Liquid photoresist in general have been difficult to work with because the coating thickness is uneven and plated through holes have plugs of resist that are difficult to remove. Pinholes, that is dirt, in the resist image necessitate inspection and quite often require a touch-up operation. Liquid film photoresist are classified as positive acting resist, negative acting resist, dry film photoresist, cover sheet, polyester, resist film, copper foil, base material. For the production of professional grade PCBs, dry film photoresists are widely used in PCB manufacture. The dry film resist is available as a composite material consisting of 3 different layers. The strong points for the dry film photoresist are uniformity, increased thickness, and ease of application. The flowchart for dry film resist processing is as given below. Pre-lamination cleaning and drying, that is pre-baking. Dry film lamination. Exposure, that is printing. Developing and drying, that is post-baking. Inspection and touch-up. Stripping. The photopolymer layer is sandwiched between a layer of polyester, that is mylar film, in one side and on the other side a polyolefin film. As the board passes through the laminator, the photopolymer is applied to the board surface by using heat and pressure. In the lamination process, the polyolefin sheet is removed just prior to lamination. The polyester cover sheet, that is film, serves as a protection from fingerprints and foreign particles. The protective layer is removed only before the development of the exposed resist. The polyester and polyolefin layer allows the dry film resist to be wound into rolls and packaged in lengths of 122 to 305 meter, that is 400 to 1000 feet. Screen printing. This video explains the process of screen printing and the materials needed for screen printing. The photographic image is transferred to copper-clad laminate by the screen printing technique. This technique has been used for a long time for printing cloth, panels, and so on, and reaches its maximum degree of accuracy when applied to PCB manufacture. The technique is particularly adopted for low-cost print and etches and plated printed boards. A screen comprises an aluminum frame, mesh, emulsion, and adhesive bonding. The emulsion is removed by a photochemical process where deposition is required. The flexibility of the emulsion creates a good gasket against the PCB and aids print definition. Screen printing is basically a stencil operation which depends on the transfer of resist to the copper-clad laminate surface using a stencil image of the circuit design. Screen printing. The stencil is firmly attached to the surface of a silk, nylon or stainless steel screen. A liquid resist material is forced through the open areas of the screen mesh that are not protected by the stencil onto the copper-clad substrate. By the pressure of a squeege, the top surface of the screen is wiped and the squeege pressure deflects the screen downward in point contact with the substrate. As the squeege passes a given point, leaving screen ink behind, screen fabric tension snaps the screen back. Screen frame. The frame, a screen fabric of uniform mesh or opening, is stretched, which provides a support. Normally, two types of flat screen frames are used, rigid type and adjustable type. Rigid type frame. Adhesive pasted part, rigid aluminum frame, screen mesh. Adjustable type frame. Floating bar, bolt with wing nut for adjusting tension. Side of frame. The frames are made of strong materials like wood, aluminum alloy, stainless steel or plastics. Aluminum alloys and stainless steel frames are the most widely used frames in the PCB industry. Due to its absorption of water during the process, wooden frame is not widely used, even though the weight of a wooden frame is comparatively lesser, leading to a bend tendency. Normally, aluminum alloy is used for rigid type and stainless steel frame for stretchable type, that is, variable tension frames. The frame size is usually 400 meter into 400 meter. However, only 10 to 25% of the screen area should be utilized. Screen cloth. The woven mesh fabric used in screen printing may consist of stainless steel, silk, polyester, nylon or similar material. The threads of the above fabrics are classified into the following two types. Monofilament. Monofilament is a woven with single thread fibers. The examples are stainless steel and phosphor bronze, nylon and polyester. Multifilament. A multifilament cloth is woven with more than one fiber or many separate fibers. The examples of multifilament are silk and polyester. Screen fabrics are classified based on mesh counts, mesh opening, and the percentage of open area or ink coverage area. The screen fabric mesh is classified according to the number of threads or wires, that is openings, per linear centimeter thread or wire diameter. The larger the mesh classification number, the more wires per linear centimeter, and therefore the smaller the openings, the finer will be the resulting circuit image. But sometimes it will be more difficult to push the screen ink through the small screen openings onto the substrate surface. Multi-filament polyester is not used in circuit printing, which is used basically in ceramic printing. Monofilaments like polyester and stainless steel are generally used since it gives more passage for inks to penetrate deposits better and to give uniformity of color or paste. It produces less drag during the squeezing process, and so monofilaments are used for screen printing with direct emulsion and indirect emulsion methods. Typically, maximum particle size should be no longer than 1/3 of the mesh opening to prevent jamming. The thickness of ink deposit is controlled by the fabric material. For determining the correct mesh count of the fabric, theoretically, color volume is used. The theoretical color volume is the amount of ink held in the fabric prior to the passage of the squeege during the printing stroke, and it is determined by the thread count, thread thickness, and mesh opening. The edge definition of the image produced by the printing screen varies according to the mesh opening M0 and thread thickness D. The printing fabrics differ according to the quality of the threads, that is HD, T, S thread types. S. Thin mesh grades. HD. Heavy duty mesh grade. T. Medium mesh grade. The most commonly used thread types for screen printing in the PCB industry are T-type and S-type. Screen preparation. The screen is prepared by considering various factors such as the image transfer line and space requirement, panel size, fabrication process, run length, etc. It is followed by properly selecting the fabric type, mesh size, frame stencil, and ink. Once this process is done, the fabric is cut several centimeters long, then the frame molded into the rails of the frame with staples and adhesives under maximum tension uniformly applied by hand. The correct stretching of the fabric is very important in the process of circuit printing, else it will cause poor registration of the printed detail, color pattern, off-contact printing, loss of open mesh, and loss of ink passage. During the stretching, the frame should be rigid and the threads should be parallel or at an angle of 45 degrees to the sides of the frame. The sides should not bend during stretching. The tension of the screen should be maintained between 10 to 15 Newton per centimeter. The screen is stretched over frame in the following ways. The fabric is stretched permanently using special adhesive or nail on the frame, and in this case, the tension is not adjustable. For stretching, equipment like pneumatic system, that is using air pressure containing pneumatic clamps, can be used. The fabric can also be stretched by using a floating bar frame. The screen tension is adjustable in this case. Once the stretching is complete, the tension of the fabric is measured using the tension gauge. The meter is placed on any part of the screen fabric and the reading becomes available on the gauge dial. The gauge measures tensions from 7 to 50 and the dial is calibrated in newtons per centimeter. The stretched frame is removed and the fabric is thoroughly cleaned, and with a proper degreasing agent it is degreased. The degreasing agent should not affect the screen fabric. It can be 20% sodium hydroxide or disodium phosphate or any other degreasing solution recommended by the screen fabric manufacturer. After the screen is degreased, the screen is rinsed with warm or cold water. The screen is then dried by using a fan or a blower which gives hot air. The screen is now ready for printing. Squeegees. The squeege used in the screen printing process consists of an elastomeric material such as urethane or a strip of rubber which is mounted on a wooden or an aluminum holder. Types of squeege: one-hand squeege, two-hand squeege. Application of squeege. The material is available in various thickness consisting of different compositions of natural and synthetic, that is polyurethane rubber. The flexibility of the rubber is measured in terms of durometers, that is hardness. Usually 40 to 50 durometer rubber is used in textile industries for printing and 70 to 80 durometer rubber is used in the PCB printing process. The sharpness of the squeege is very important for printing. Line sharpness, uniform ink coating thickness and the edge definition depend upon the squeege's sharpness. The sharpness is reduced after continuous operations as the edges becomes rounded. Hence, it is required that the sharpness of the squeege is to be maintained. This is done by sandpaper or any other abrasive material. It is important that the over sharpness of the squeege also damages the screen. Milling. This video describes the process of milling. Milling is a commonly used operation which is used for the process of clean cutting of PCBs and for obtaining good edge finish and overall dimensions with a high degree of accuracy. The generally used cutting speeds are in the range of 1000 to 3000 rpm. They usually employ straight or spiral tooth HSS, that is high speed steel milling cutters. However, in the case of glass epoxy laminates, the use of tungsten carbide tools is preferred due to their long life. During milling, the PCB must be given strong support with backing plates in order to avoid delamination. Fabrication of double-sided PCB. This video explains in detail about the fabrication steps that has followed to produce double-sided PCB. The processing techniques followed for fabricating single-sided boards are applicable to most board processing. However, the process for producing double-sided printed through holes is more complex than the print and etches method. Schematic diagram. The schematic diagram, also known as circuit or logic diagram, represents the electronic components and its connections clearly is the most readable form. The schematic diagram is developed while taking into consideration the specifications of components, interaction between components, that is especially timing and loading, physical packages and arrangement of connector pin outs. The circuit diagram references each part on the printed circuit board with the designator, example IC4, and also the pin numbers for each connection. Artwork generation. The components and connections in the PCB layout are derived from the circuit diagram, that is schematic diagram, and it is physically placed and routed by the designer in order to get the best results in terms of board size and its manufacturability. The PCB layout defines the final physical form of the circuit, and once the layout is completed, labeling details are finalized. When the PCB layout is complete, the track layout information will be provided on self-adhesive type crepe material tape, which stuck on a plastic sheet such as polyester. The layout or artwork is usually enlarged one, which will be in the range of 2 to 4 times to improve accuracy. Panel preparation. Laminate sheets with copper cladding on both sides are cut to size as per requirement. Even though the size of the panel depends upon the capacity of the plating equipment, the preferred size for many manufacturers is 305 into 406 mm. The laminate commonly used is 1OZ by FT square copper foil, epoxy glass type or FR3. Hole drilling. The double-sided board is first drilled, which is followed by the removal of any burrs by manual or automatic means. The board is then thoroughly cleaned to remove chips of glass fiber and resin. Cleaning is usually done at the high pressure of order of 20 to 60 atmosphere by using a jet of water. Electroless copper plating. Initially, by immersing the board in a solution of stannous chloride, it is sensitized. The stannous ions are absorbed on the board surface and whole walls, particularly onto the exposed resin. Once the above process step is completed, the board is immersed in an acidified solution of palladium chloride. The palladium ions are reduced to the colloidal state and form a thin layer. This layer catalyzes electroless copper deposition. Electroless copper deposition bath solution contains copper sulfate, sodium hydroxide, formaldehyde, a reducing agent and other special additives. Here, the copper ions gets reduced to metallic copper. This results in deposition of copper. The thickness of the copper layer is determined by the duration of the board in the solution. Usually, a thickness of about 40 microns of copper is built up on the base copper and on the whole walls. Image transfer, that is photolithography. Both sides of the board are covered with a thin layer of a photoresist, which may be either positive or negative and may be solid or a liquid. A solid negative working resist is mostly used. The image transfer process occurs with the photoresist removed from the area, where the tracks are to be kept, resulting in a reverse process of the print and etch process. The copper areas will remain on the finished PCB and the whole walls are unprotected, and all other areas are covered by the hardened photoresist. Developing of both sides is usually done in an automatic spray machine. Tin lead plating. By immersing the board in an electroplating bath, the exposed track areas are electroplated with tin lead alloy. All conductive areas, that is, all the conductors required on the PCB and within the holes, is plated to a thickness of about 20 to 25 microns approximately, which should not be less than 10 microns. This metal is used as a resist in the etching process. Etching. The etching process is the core of the PCB manufacturing process, which is based on subtractive method. Etching process involves the removal of copper from undesirable areas in order to achieve the desired circuit patterns. Etching is usually done by the immersion, bubble, splash or spray method. The spray etching method is the most common. In spray etching process, the etchant is pumped under pressure from a tank to the nozzles which splash the etchant on the board. The etchant used should not attack the tin lead alloy. Once the etching process is done, followed by the application of surface finish coatings such as hot air leveling, solder masking, and organic surface protectant, the selective areas of the board can be plated with precious metals such as gold or nickel. Testing. The board is then finally inspected and tested as per the user specifications. There is a possibility to get some repairs or rework on the finished boards. Plating process. This video explains in detail about the plating process. In printed circuit boards, copper is used for interconnecting the components on the substrate. Even though it is a good conducting material on the PCB to form the conducting track pattern, if exposed to atmosphere over a long period of time, it is liable to tarnish due to oxidation. It undergoes corrosion and thus loses its solderability. Therefore, various techniques are used for the protection of the copper tracks and via holes and printed through holes, that is PTH. They are organic lacquer coating, oxide coating, plating. Organic lacquer coating is not suitable for long-term usage due to variations in thickness, composition and curing cycles. Though it is simple in application, it can also bring about unpredictable deviation in solderability. Oxide coating can be used to protect the circuit from corrosion, but it fails to preserve the solderability. Plating or the metal coating process is a standard practice to ensure solderability and protect the circuit from corrosion. So it plays an important role in the PCB manufacturing of single-sided, double-sided and multi-layer, that is PTH boards. In particular, plating a solderable metal over the tracks has now become a standard practice to afford solderable protection to the copper tracks. Plating process of PCB. Flowchart of plating of PCB. There are two standard methods to get metal buildup onto the circuit traces and the holes: pattern plating and panel plating. Pattern plating. This is the process wherein only the desired circuit pattern and holes receive copper buildup and etch resist metal plate. During pattern plating, the circuit lines and pads increase in width on each side about as much as the surface thickness during plating. Pattern plating basically involves masking of most of the copper surface and plating only the traces and pads of the circuit pattern. Due to the reduced surface area, a much smaller capacity current source is generally needed. Pattern plating consumes less copper from the anode bank and requires the removal of less copper during etching. thereby reducing bath analysis and maintenance. The disadvantage of the technique is that the circuit pattern is required to be plated with either tin or lead or an electrophoretic resist material prior to etching and then stripped prior to solder mask application, which increases the complexity and adds another set of wet chemical baths to the process. Panel plating. This is the process where the entire surface area and the drilled holes are copper plated, sloped off with resist on the unwanted copper surfaces and then plated with the etch resist metal. When you etch a panel plated board, you end up removing most of the material that you plated. So, the burden of extra erosion of the anode banks is exacerbated by an increased copper loading in the etchant. Plating techniques. This video explains in detail about the plating techniques following in the manufacture of PCB. Plating. Plating is needed on the whole surfaces of PCBs in order to facilitate conduction in the conductive path via holes. Electroplating and electroless plating are the two plating processes commonly used. Electroplating requires that the coated surface is conductive, while electroless plating does not require a conductive surface. The walls of the via holes and insertion holes after drilling consist of epoxy glass insulation material which hinders conduction. Therefore, electroless plating must be used to provide conductive path, and also the copper coating thickness is increased by means of electroplating process. Plating techniques: immersion plating, electroless plating, electroplating, electroplating. Electroplating is a process in which a metal is deposited on a conductive surface by passing a direct current through an electrolytic solution containing a soluble salt of the metal. When a unidirectional current is passed through a solution, it results in movement of the charged particles through it. These particles are called ions, and the terminals which are used to pass the current into the solution are called electrodes. The combination of the two electrodes and the solution form is known as electrolytic cell. The other electrochemical terms associated with electroplating are listed below. Anode. The pole or electrode at which the chemical reaction of oxidation takes place is called the anode. It is a positively charged electrode. During electrolysis, positive ions are formed at this electrode. Anion. This is a negatively charged radical. On electrolysis, it is attracted towards the anode. Cathode. The electrode or pole at which the chemical reaction of reduction takes place is called the cathode. It is a negatively charged electrode. During electrolysis, negative ions are formed at this electrode. Cation. This is a positively charged radical. On electrolysis, it is attracted towards the cathode. Electrolyte. This is a conducting medium in which the flow of current is accompanied by the movement of ions. For electroplating, the electrolyte must contain dissolved salt of the metal that is to be deposited. In the electrolytic cell, the metal to be plated is used as the cathode. The anode in the cell can be the same as the metal to be coated on the cathode or any other inert metal having good conductivity. The reaction which takes place at the junction between the electrolyte and the electrodes is called electrolysis, which is accompanied by the transfer of electrons. Basic process. The PCB to be electroplated is first cleaned thoroughly to make it free from oil, grease and foreign particles. The cleaned PCB article is used as cathode in an electrolytic solution. The electrolyte is kept in an electroplating tank. The two electrodes, anode and cathode, are dipped in the electrolyte. Let us see an example for electroplating. Electroplating of silver, that is silver coating on a spoon. When direct current is passed through the electrolyte, coating metal ions migrate towards the cathode and get deposited. Most plating solutions are similar in nature. Therefore, their use and their quality of the resulting deposits would depend upon the processing variables involved. Accordingly, the deposition depends on the temperature, current density, metal ion concentration, pH, solution movement and filtration. Basic electroplating process. If the anode is made up of a metal which is the same as the metal to be deposited on the cathode, the concentration of electrolyte remains the same during electrolysis. The metal which is deposited on the cathode is removed from the electrolyte. This loss in the electrolyte is compensated since the anode dissolves in the electrolyte proportionately. If the deposition and dissolution are not equal, it will affect both the metal concentration in the electrolyte and deposition rate. Electroless plating. The procedure for electroless copper plating is complex. The electroless copper plating process will vary depending upon the size and type of the substrate and the production throughput demands. To ensure that electroless copper plating is done properly, the fabricant must understand the intricacies of the plating chemicals and equipment along with the substrate material used in the PCB. In general, the following operations are carried out in sequence to complete the electroless plating on a PCB. Laminate deburring, laminate cleaning, water rinse, micro etch or etch back multi-layer boards, acid rinse, sensitizer dipping, activator or catalyst treatment, accelerator dip. Electroless plating, that is copper electroless plating. Laminate deburring. The drilled board surfaces are cleaned by using a deburring machine and a 320 grade silicon carbide brush. Deburr is a mechanical process that removes the raised edges of the metal or burrs surrounding the holes that occur during the drilling process. Any debris that may be left in the holes is also removed at this time. Laminate cleaning. In this step, the drilled through hole is cleaned in an alkaline cleaning solution to remove any fingerprints, oils, grease layers and epoxy smears. The bath contains mixed alkali chemicals. The temperature of the bath is maintained at 60 to 70 degrees Celsius and the dipping time is about 20 minutes. Water rinse. After each process step, the substrate is rinsed to ensure that none of the chemicals is transferred to the next bath. Each step relies upon the chemical reaction within itself and can contaminate the reaction of another bath. Microetching. This is done in persulfate acid, sulfuric acid and hydrogen peroxide and stabilizers. It is used for microetching or cleaning of copper surfaces already existing on the laminate. In the process, some amount of copper gets removed from copper surfaces and gets dissolved in the solution used to provide a uniform surface. The importance of microetching is that it ensures a uniform metal surface and increases the bonding between the copper layers by roughing up the surfaces. This also gets rid of any contaminants that may impinge oxidation. The etch back method is used only for multi-layer PTH processing to clean the whole walls. Acid dip. The sulfuric acid dip rids the board of any remnants from the micro-etching process. If the substrate is put in the sulfuric acid dip, it must be rinsed before the pre-catalyst stage. 20% sulfuric acid is used for the dipping process. Sensitizer dipping. This is the pre-catalyst stage which prepares the substrate for the next step, that is catalyzation. This bath is a combination of salt and acid and is a mixture of stannous chloride and hydrochloric acid. The bath can also act as a preheater for the activator stage. Activator catalyst treatment. The activator or catalyst is a surface treatment process that makes the substrate surfaces and whole walls amenable to copper. In this, the sensitizer and activator are mixed in a bath to get a mixed catalyst solution which produces a catalytic film of palladium. The catalytic film is produced only on the surface of the insulator, the resin and tiler, but the copper foil of laminate remains inactivated. The thin palladium film improves adhesion between the plated copper and the base copper. The sensitizing step involves immersion of the board in an acidic solution, that is sensitizer, containing stannous ions which are absorbed by the surface of the resin. According to a reduction reaction, the stannous ions reduce the palladium ion. According to an oxidation reaction, the stannous ions are oxidized to stannic ions. The tin is removed in the next step, leaving the palladium layer ready for copper deposition. The temperature in the activator or catalyst tank is extremely important. To maintain the even temperature throughout the bath, an air pump is used in this bath to agitate the solution. The board must be rinsed thoroughly so that it does not contaminate the accelerator or post-accelerator bath due to the volatility. Generally, the PCB is subjected to 2 rinse cycles. Accelerator dip. Accelerator is a strong acid or alkali which is used to remove the colloidal tin from the activator bath. Remnants from this bath can neutralize the electroless copper plating bath, therefore rinsing is again very important at this stage. Electroless bath. The copper is plated on the drilled holes and the substrate surface in the electroless copper bath. This can be done as a subtractive or an additive process. The subtractive process involves plating a substrate with conductive copper and then exposing it to electrolytic plating. Then the substrate's circuit pattern can be created by masking and etching. Deposited copper by chemical deposition method. In the additive process, the substrate is exposed to a copper process only once. The additive process metallizes the substrates through holes and the circuitry pattern at the same time, thereby eliminating the need for electroplating. Deposited copper after tin plating process. Produce the finer lines demanded by surface mount technology as compared to the boards produced by using the standard etching process. Ability to metallize high aspect ratio holes uniformly. Etching. This video explains the process of etching and its types. The final copper pattern is achieved by selective removal of all unwanted copper to retain the desired circuit patterns using this process. Pattern transfer by etching. The following are the commonly used etching methods: chemical etching or chemical machining, electrochemical etching or chemical milling, and mechanical etching, that is by milling. Chemical etching or chemical machining. Electrochemical etching or chemical milling, and mechanical etching, that is by milling. . The etching process is performed by exposing the surface of the board to an etchant solution which dissolves the exposed copper areas, thereby leaving the desired conductor pattern on the board. Different types of etchant solutions are in use. Main among them is the following: ferric chloride, cupric chloride, chromatic acid, alkaline ammonia. The choice of suitable etchant for a PCB production depends on the factors like compatibility with etch resist, etching speed, copper dissolving capacity, etchant price, and pollution characteristic. The etching process can be performed by simply immersing the board in an etchant solution and then agitating. This is difficult to control the process and can result in non-uniform etching. Example of etchant: ferric chloride. Ferric chloride etching solutions are widely used in the print and etch process in the PCB industry. Ferric chloride is the oldest and the most common etchant, which normally comes in crystal form. The crystals are dissolved in deionized water to achieve its desired concentration in the solution. This is typically 500 grams of ferric chloride in 1 liter of water. Ferric chloride has a high etch rate and high copper dissolving capacity. It is used with screen inks, photoresist, that is wet film and dry film, and old plated boards. It is not suitable for tin or tin lead plated boards, since ferric chloride etchants attacks tin. This etchant is an aqueous solution of 28 to 42% by weight of ferric chloride. It operates over a wide range of concentration but is most widely used at about 35%. The ferric chloride solution has free acid due to the following hydrolysis reaction. FeCl3 plus 3H2O gives FeOH3 plus 3HCl. In order to prevent the formation of insoluble ferric hydroxide, an excess of hydrochloric acid up to 5% by weight is usually added, which prevents the spontaneous hydrolysis of FeCl3. At the initial stage of file etching process, the concentration of copper dissolved is high due to file high concentration of ferric chloride. As the ferric chloride in the solution gradually gets depleted, the etching time increases to the extent correspondingly. After some time, the solution has to be discarded and replaced by a fresh solution. When the etchant is sprayed perpendicular to the copper surface, better dissolution of copper occurs and the board is moved. The rate of dissolution of copper depends upon file ferric chloride concentration, temperature and agitation rate. During etching, the ferric ion Fe3+ oxidizes copper to cuprous chloride, that is CuCl. Then the cuprous chloride further oxidizes to cupric chloride as CuCl2. Cu plus FeCl3 gives FeCl2 plus CuCl. FeCl3 plus CuCl gives FeCl2 plus CuCl2. CuCl2 plus Cu gives 2CuCl. By crystallization, ferric chloride etchant can be regenerated by passing chlorine gas and to recover copper from the ferric etchant. Ferric chloride regeneration and recovery process. Etching techniques. Etching arrangements can be done in the following ways: simple batch production etching, continuous feed etching, open loop regeneration, closed loop regeneration. The etchants may be applied to boards in one of the following ways: immersion etching, bubble etching, splash etching, and spray etching. Spray etching is the most commonly used technique due to its high productivity and fine definitions. Spray etching. Commercially, the etching of PCB is done in spray-type etching machines. There are two types of spray etching techniques. They are horizontal spraying, vertical spraying. Horizontal spray etching system. Vertical spray etching system. In spray etching, the etchant is pumped via a pipe network under pressure from the sump to the nozzles, and from there it is splashed onto the boards. Spray etching machines offer high etching uniformity and fast etching rate. The high etching uniformity is achieved by spraying through a number of equally distributed nozzles in ring supply, which results from the fresh flow of the etchant over the boards. Etching profiles. Under etched profile, ideally etched profile, over etched profile. This figure shows different etching profiles. However, it is important to control the etching process. Insufficient etching will result in excess copper being deposited on the board, which leads short-circuiting between the tracks. The use of etchant solution should be carefully controlled as it becomes contaminated with copper, that is dissolved, thereby the performance of the PCB affects more. By making use of electrochemical extraction methods, the copper contained in the exhausted etchant solution can be regenerated. After completion of the etching process, the etch resist material is removed chemically, which leaves the PCB with the desired copper pattern. Shearing. This video explains what shearing process is and what its instrument looks like. Shearing is the first mechanical operation carried out on PCBs to give them proper shape or contour. Shearing process. It is basically a cutting method applicable to all kinds of base materials, generally of less than 2 mm thickness. If the board is greater than 2 mm thickness, shearing will lead to the edge finish, which is coarse and unclean, and therefore the method becomes unacceptable. Laminate cutting by shearing can be done either by manually operated or by motor-driven machines. Both have common constructional features. A shearing machine normally has an adjustable set of shear blades. The blades are of rectangular shape in which the lower blade has a free angle of about 7 degrees. The cutting length capability is available up to 1000 mm. The lengthwise angle between the blades is generally preferred between 1 to 1.5 degree, though for glass epoxy materials up to 4 degree can be used. The angle between the shear blades depends upon the thickness of the material to be cut. The thicker the material, the greater will be the angle. If the gap between the plates is too wide or the shear angle is too high, feathered cracks appear while cutting paper-based materials. In case of glass epoxy laminates, even though cracks do not develop due to flexural strength of the material, if the shearing angle is too wide or the blade gap is too large, the material does show deformation. For obtaining a clean edge finish in paper-based materials by shearing, heating the material in the range of 30 to 100 degrees Celsius is helpful. In order to obtain a clean cut, the board must be firmly pressed down with a spring-loaded hold-down device to prevent the unavoidable shifting of the board during shearing. Also, parallax errors, which may result in errors up to 0.3 to 0.5 mm, should be minimized, and precision stoppers should be used for alignments of the corner marks. Shearing machines are available to handle jobs of various sizes and to offer accurate dimensional reproducibility. There are larger machines which is able to cut several hundred kilograms of base material per hour. Punching. This video explains the process of punching. Punching of holes in PCBs is also one of the machining operations like hole drilling. In general, large holes are easier to punch than small holes. Punching is used in the high volume production of consumer type PCBs made of paper phenolic and paper epoxy laminates. Punching of holes. The other disadvantage of punching is the pad delamination and laminate cracks on adjacent holes. In addition, instead of rough surface, punching results in holes of conical shape. They are not compatible with professional PCB plated through hole process, where high surface smoothness is desirable. Along with the above laminations, hole punching also has some advantages. They are very high production rate and low operation cost because a large number of holes can be punched simultaneously, high accuracy and repeatability of the hole position. In single-sided boards, the punching is done on the copper foil side. When paper-based laminates are to be punched, ensure that the materials are resilient and their tendency to spring back will result in a hole slightly smaller than the punch which produces the hole. The differences are due to the thickness of materials. So while making dies, some positive tolerance is required to obtain the correct hole size. Generally, the diameter of the punches should be 0.1 to 0.12 mm bigger than the desired hole diameter in boards of 1.6 mm thickness. The typical diameter tolerance of punched holes is plus 0.1 mm. For precision work, there must be a close tolerance between punch and die. When carrying out punching operations, always pierce with the copper side up. It is not advisable to use designs with circuitry on both sides of the board, which leads the lifting of pads. Also, if the distance between the holes is too small, there is a chance of cracks appearing between holes. In such cases, the process should be planned such that the piercing is done before any copper is etched away. The presence of the copper foil has a reinforcing effect and helps in eliminating cracks. Drilling. This video explains the process of drilling in PCB. Drilling operation is one of the important mechanical processes in the manufacture of printed circuit boards. Its purpose is to provide component lead mounting precisely and with structural integrity to establish an electrical interconnection between the top, bottom, and sometimes intermediate conductor pathways. After the drilling process, the drilled circuit board undergoes various processes like plating, imaging, etching, and solder plating. Therefore, care is needed to obtain a good surface on the drilled hole, and hence its quality assumes great significance. The quality of a drilled hole depends upon various factors such as processes including machine accuracy, drilling techniques and operator skill in control, and evaluation of hole quality and drill bits. Requirements in drilling. A good drilling technique must satisfy the following conditions: consistent high quality, lower cost and simple storekeeping, perfect through-hole plating, greater production and smaller diameter, shorter distance between the holes. The important steps in the drilling process are typical steps in drilling. High quality drilled holes are obtained when all the processes are properly implemented. Those boards can be plated directly, thereby eliminating other processes such as deburring, desmearing and etch-back. This results in process simplification, higher yields and lower cost. The root cause for 85% of all circuit board failures can be traced back to drilling. On examination of the entire board manufacturing process, it proves that many post-drilling operations are corrective measures designed to overcome shortcomings in the drilling process. Addressing problems that results from the drilling. Use of mechanical scrubbing to remove burrs, chemicals to remove resin smear and bonded debris, etch-back to expose glass fibers, acid or alkaline cleaners to remove contaminants. PCB assembly process. This video explains about the assembling process of components in PCB and its types. Placement of components. The following are the main guidelines used in the placement of components of PCBs. Components should be placed such that they can be accessed easily. Components used for internal adjustment such as potentiometers, trimmers, and switches should be located on the board edge so as to get easy access. Component placement for easy access. Components with a metal case should be free and not be obstructed by any other components, that is adjustment by screwdriver. Distributed mechanism for heat producing components. Heat producing and heat sensitive components are regularly distributed over the entire board area. Avoid the locally overheated area. The airflow arrangement should have free and unobstructed path. It flows in vertical direction from bottom to top. Arrangement for heat producing components. Heat producing components as well as heat sensitive components should be placed with a proper care, which can be arranged. Mounting of components. The following are the main component mounting considerations. All components of the same type should be mounted in the same direction and with orientation. The components should be mounted either horizontally or vertically. Heavier components are used with adequate clamps or clips. To avoid mechanical overstressing, solder joints should be as fine as possible. Sufficient free space should be provided for card guides and card handle. The component getting heated and components sensitive to heating should be placed apart. Component assembly and precautions. It is important to assemble the components properly and precisely on the PCB. The following precautions must be taken during the assembly of components on the PCB. Components-led precautions. A bending tool is used for bending the component lead. If the component lead is not properly bent, poor quality leads bending. Uniform component mounting. In assembly, testing and servicing points of view, uniformity in orientation should be maintained. Top view of uniformly placed horizontal and vertical component mounting. Correct or incorrect lead bending for two lead components. Horizontally mounted components should not touch the PCB to avoid lifting of solder. Correct or incorrect vertical mounting. Vertically mounted components should not touch the PCB in order to avoid strain or solder joints. Use of a spacer for separation. Heat producing components must be separated from the PCB with the help of a spacer. Insulation for jumper wires to avoid short. When a jumper is used on the PCB, then the insulation must be provided across the conductors. Transistor mounting with spacer. Transistor mounting with sleeves. Soldering. This video explains about the process of soldering in PCB, types of soldering and how it is tested. Solder, solder wire, solder flux, PCB. A process of joining metal parts by making use of any of the various fusible alloys, that is solder, is known as soldering. Soldering can be done with a tool known as a soldering iron or soldering gun, but the most commonly used tool is a soldering iron. A soldering iron consists of an insulated handle connected via a metal shaft to the bit. The face of the bit makes a contact with the component parts of the joint and the solder, which needs to be soldered, and heats them up. The electrical heating element is located in the hollow shaft or in the handle and may be thermostatically controlled to give a preset temperature in the bit. The bit of a soldering gun stores heat and conveys it from the heat source to the work. Sometimes it may be used to remove the surplus solder from joints. The bit should be perfectly wetted, that is tinned, so as to encourage the flow of solder into joints. All soldered joints must be cleaned before the metal parts to be joined. That is, when the components lead to be fitted up to the point of joint and heated for soldering the lead. Thus, a flux is applied and then the filler of the solder metal is applied to the point of joint. The following steps are used in soldering with the help of a soldering iron. Step 1. Parts to be joined are cleaned and fluxed and assembled for soldering. Step 2. Soldering iron at soldering temperature is held on the workpiece to heat them. Step 3. The solder is applied to the bit where it should melt. Step 4. When the joint appears to be sufficiently filled, the soldering iron is removed and the joint is allowed to cool down undisturbed. The time required to keep soldering firm on the work is entirely dependent on the nature of the joint and characteristics of the soldering iron. Soldering techniques. This video explains about the process of soldering in PCB, types of soldering and how it is tested. Mass soldering, dip soldering, drag soldering, wave soldering, reflow soldering. Mass soldering. Mass soldering is a technique that is used in making large number of joints or soldering using a solder bath, both as a source of heat as well as solder metal. In the most important soldering techniques, a kind of immersion or contact with a molten solder bath is used. In addition to high productivity, a more rigorous control is possible over all individual stages of soldering using the mass soldering technique. This technique is widely used in electronics industries, particularly for assembling number of PCBs at a time. Dip soldering. Using dip soldering, cleaned and peel assembly is lowered vertically to clean the solder surface until it makes contacts. The assembly is then immersed in a solder to the required depth. The surface is wetted with the solder, and wherever the intersections are sufficiently narrow, the solder penetrates and is retained between them by capillary forces. Angled dip makes easy escape for air when lowering there are vapors, and when lifting, better solder drainage. The following are the specifications of soldering material and bath. Solder container metal is made of cast iron or steel. Bath's temperature is between 220 degrees Celsius and 280 degrees Celsius, that is for binary tin lead alloys, and 340 degrees Celsius and 400 degrees Celsius for lead-rich alloys. Solder composition has 60% SN, 40% PB or authentic alloy. Drag soldering. A conveyor system is used to move the PCB so that it passes successively over a fluxing station, a flux dragger or a preheating stage, and then over the surface of a long and narrow solder bath. The board is lowered at a small angle and then moves horizontally along the solder surface before being withdrawn at a small angle to help solder drainage. Before the PCB makes a contact with the solder surface, a horizontal scraper bar moves along the positive path to remove oxide films and flux residues, leaving a clean solder surface to enhance melting. Wave soldering. The name wave soldering is derived from the use of waves of molten solder to attach metal components to the PCB. The process uses a tank to hold a quantity of molten solder. The components are inserted into or placed on the PCB, and the loaded PCB is passed across a pumped wave or waterfall of solder. The solder wets the exposed metallic areas of the board, creating a reliable mechanical and electrical connection. The process is much faster and can create a higher quality product than manual soldering of components. Wave soldering is used for both through-hole PCB assemblies and assemblies of SMDs. In the latter case, the components are glued by the placement equipment onto the PCB surface before being run through the molten solder wave. A standard wave solder machine consists of 3 zones: the preheating zone, the fluxing zone, and the soldering zone. The cleaning zone, that is depending on the type of flux applied. The basic equipments used during the process are a conveyor that moves the PCB through different zones, a pan of solder used in the soldering process, a pump that creates the actual wave, the sprayer for the flux, and the preheating pad. The boards, after passing over the wall fluxing and dragging sections, are conveyed across the crest of solder wave following a straight line path. The drainage end of the solder may be improved by choosing a potential wave form. Double-crested, flat-topped and unidirectional solder flow against the direction of the board movement. Reflow soldering. Reflow soldering is a process in which a solder material is used to temporarily attach one or several electrical components to their contact pads, after which the entire assembly is subjected to controlled heat, which melts the solder permanently, connecting the joint. Reflow soldering oven. Heating may be accomplished by passing the assembly through a reflow oven or under an infrared lamp, or by soldering individual joints with a hot air pencil. Reflow soldering is the most common method of attaching SMDs to a PCB. The objective of the reflow process is to melt the solder and heat the adjoining surfaces without overheating and damaging the electrical components. In the conventional reflow soldering process, there are usually 4 stages called zones, each having a distinct thermal profile: preheat, thermal soak, reflow, and cooling. Soldering techniques. This video explains about the process of soldering in PCB, types of soldering and how it is tested. Removal of flux. It is important to remove flux residues after cooling of the assembly to avoid corrosion during storage. Removal of flux using dilute alcohol. Corrosion flux is water soluble, example zinc chloride, so care must be taken to avoid hydrolyzing. Corrosive flux must be removed by first washing the assembly with 0.5 to 1% HCl or 5 to 10% citric or acetic acid, and then by neutralizing in dilute alkali. Non-corrosive or resin-based fluxes used for electronic assemblies can be removed with non-organic solvents. Certain flux activators are only removed by gaseous solutions such as isopropane. Ultrasonic transducers with organic or aqueous solvents are extensively used to assist dislodging flux residues during washing, with certain risk to electronic components such as electrolytic capacitor. Solderability testing. Solderability testing of components depends on the measurement of time in contact with molten solder to achieve good wetting under given conditions. The three solderability test principles are discussed below. Solder bath test, meniscus rise test, soldering iron test. Solder bath test. The rotary dip test is a standard test method, is suitable for accessing the solderability of PCB sheet metal, jigs, etc. used by electronics industry. The test procedure involves immersing a number of pre-fluxed square test pieces. The solder bath temperature are maintained at certain fixed value. The testing apparatus has a horizontally rotating spindle and a radial arm to carry the test pieces horizontally and face down across the surface of the solder bath. The portion of the non-wetted surface becomes less with increasing time in the solder bath until a time of contact is found at which the complete wetting occurs. Meniscus rise test. When a wire or sheet metal is immersed in a bath of molten solder, a meniscus of solder forms on the sample, which can be seen using a microscope. A microscope is also used to measure the height of rise of the meniscus at equilibrium or after a given period of time. This height is measure of the solderability. Soldering iron test. In situations where assembly methods require the use of manual soldering, it is sometimes decided to conduct soldering test with an iron or specified wattage, bit size and bit temperature. This gives a useful guide to the performance on the production line. IPC standards by US Institute of Printed Circuits. This video explains about the IPC standards by US Institute of Printed Circuits. IPC IM 100 Technical Manual, Specification and Standards. IPC CP 150 Copper Foil of Printed Wiring Applications. IPC FC 218 General Specification for Connectors, Electric Flat Cable Type. IPC FC 240 Specification for Single-Sided Flexible Printed Wiring. IPC D300 Dimensions and Tolerances for Single and Two-Sided Printed Wiring Boards. IPC D320 Printed Boards, Rigid, Single and Double-Sided, End Product Standard. IPC D330 Printed Wiring Design Guide. IPC C405 General Specification for Connectors, Electrical, Printed Wiring Board Type. IPC DW425 Design and End Product Requirement for Discrete Wiring Boards. IPC A600 Guide to the Acceptability of Printed Wiring Boards. IPC A610 Guide to the Acceptability of Printed Board Assemblies. IPC TM650 Test Methods Manual. IPC R700 Suggested Guidelines for Printed Wiring Board Assemblies. IPC CM770 Guidelines for Printed Circuit Board Component Mounting. IPC S804 Solderability Test Methods for Printed Wiring Boards. IPC S815 General Requirements for Soldering or Electrical Connections and Printed Board Assemblies. IPC ML910 Design and End Product Specification for Rigid Multi-Layer Printed Boards.